In this section, we'll be reviewing the concept of agonists. So we'll be looking at the chemical design and function of agonists, and we'll use the chemical design to rationalize how they function as molecules that activate receptors. Agonists mimic the natural messenger molecule and need to bind to the receptor in such a way as to activate it. Now, in that sense, a molecule that is designed to mimic the natural messenger molecule makes sense because we know that the messenger is able to bind to the receptor and activate it. But when we're designing an agonist, we need to consider three main points. We need to make sure that our drug has the correct binding groups to ensure that it can bind to the binding site within the receptor. We've got to make sure those groups are in the correct position because they've got to be able to interact with the correct groups within the binding site, and therefore we need to make sure that these groups, these two sets of complementary groups, line up to each other. And of course we need to make sure that the drug is the correct size to fit into the binding site. It doesn't matter whether the correct binding groups are present in the correct position if the molecule cannot physically fit into the binding site. And so let's just have a look at a quick example. So if we take this hypothetical neurotransmitter here, what we can see is that we have a six-membered ring that could provide a van der Waals binding site. We have an OH group which can act as a hydrogen bond donor or acceptor, and we have an electrostatic interaction here. So we have a positively charged group that could interact with a group containing a negative charge. Now all three of these molecules would be appropriate substitutes for the hypothetical neurotransmitter. All three of these molecules have a region, be it a ring or a carbon-carbon double bond, that could have van der Waals interactions. All three also contain a group able to act as a hydrogen bond donor and acceptor, and all three hold a positive charge in the same position, so they have a group which can form an electrostatic interaction with a negatively charged group within the protein. And therefore, it's important to make sure that we have the correct groups in the correct position and that they are, or the molecule is, of the correct size to enter into the binding site. If we have all of this, then there's a good chance that our molecule will be able to bind to the receptor and activate it. So do we need all of the binding interactions that the natural messenger molecule uses? Well, here we have our hypothetical neurotransmitter again with a van der Waals binding interaction site, a hydrogen bond site, and an electrostatic interaction site. So we could take this and produce a molecule where we've taken out our source of van der Waals interactions, we've eliminated our hydrogen bonding group, and we've also eliminated our group that holds a positive charge. Now we could also try just removing the group that is able to have a hydrogen bond, and we could test all of these and see how effective they were in activating the receptor. Now this is what would happen if we took the molecule where we've removed all of our possible binding interactions. This molecule would not have enough remaining interactions to be able to have an induced fit within the binding site. So we can see here the van der Waals interaction would be very weak because we've eliminated that aromatic ring. There's no hydrogen bonding possibility, and we've removed the electrostatic interaction as well. Now, however, if we took out just one key interaction, we may have a molecule that can still bind and activate the receptor, albeit not as strongly. So here we still have the van der Waals interaction and the electrostatic attraction as well. However, neurotransmitters are known for being able to bind to the receptor, activate the receptor quickly and efficiently, and then leave the binding site quite quickly. And so if we remove the binding interactions or binding groups from these molecules, we're likely to interfere with this process. Now that doesn't mean that our agonist must exploit all of the same binding interactions that our natural messenger does. This just means that we need sufficient interactions to be able to activate the receptor. So we have to strike a very fine balance if we want to remove binding interactions from these molecules. We have to have that balance between still being able to activate the receptor and bind strongly and removing those chemical groups that are responsible for the binding interactions. And even if we design an agonist with the correct binding groups, if they are positioned incorrectly, then the receptor will fail to be activated. So this comes back to point 2 out of the 3 things we must consider when designing an agonist, that we must have the right groups in the right position and the molecule must be of the correct size. So if we take our hypothetical neurotransmitter again, and we can see that this has 3 binding interactions, one here as a van der Waals interaction, one as a hydrogen bonding interaction, and one as an electrostatic attraction. If we take another molecule where we have changed the position of the hydrogen bonding group, so we've changed it from being here to being one carbon further away, what we can see when we put this into the binding site is that we will only have 2 interactions. The hydrogen bond will not be able to form. And so we've still got the same groups, but we can't form the same binding interactions. Now, this is something that is more of a problem when we come to different enantiomers of the same molecule. And so here we have one enantiomer, and here we have the binding site. Now this is able to form 3 interactions within the binding site and have this very strong binding interaction. However, if we take the mirror image of this molecule to give us the other enantiomer, what we can see if we put this into the binding site is that it changes the position of the hydrogen bonding functional group. So it changes the position of our OH group. And so this OH group is now directed away from the amino acid side chain that is able to form a hydrogen bond. And so even when we have exactly the same chemical groups, if we put them in the wrong place, we're not going to form those essential binding interactions. Now this can either be caused by intentionally changing the position of the groups to design a second molecule like we have here, or it can be caused by chirality. Both of these different approaches end up with the same result, in that we have fewer binding interactions available to cause that induced fit within the receptor. Now the presence of all of the required binding groups in the correct positions is critical for agonist action. Now we can change some of the binding interactions that we have. So for example, we could change a functional group so it binds with a different site within the protein, binds with a different side chain, but we still need to make sure we have a strong interaction. Now if the agonist doesn't fit into the binding site, then activation of the receptor will not occur at all. And so what we can see here is if we have a molecule that is too large to enter into the binding site, it doesn't matter that we still have our van der Waals region, our hydrogen bonding group, and our group capable of having an electrostatic interaction. If the molecule cannot fit into the binding site at all, then all of that other consideration is rendered pointless. We've got to have our molecules of the correct size to be able to fit into the available space. And they also need to be the correct shape to allow binding groups to align with the regions within the target. So we've got to make sure we have the right chemical groups in the right positions and the molecule is of the correct size to be able to enter into the binding site and activate the receptor. And if we have all of those 3 factors correct, we have a molecule that is very likely to act as an agonist. Now in the next section we will review antagonists. Now these are molecules which block receptor activation. Now this is the opposite purpose to having agonists when we want to activate the receptor. And there are some key differences in the molecular design of antagonists versus agonists that we will cover.